really honored to be here, closing out PyData Córdoba. And I have a great time these past 3 days. And congratulations to you all for surviving the conference. So I hope you survive this talk as well, because I think I would probably go over time. So to start, first, just a little bit about myself. All right, there we go. So I actually started out as a psychologist. Started out as a psychologist, and at the time I exclusively used SPSS. And then afterward, I kind of slightly changed field to study, in my PhD, I do research on kind of cognitive psychology, and I look in mostly on like how human vision works. So basically how we recognize faces, objects, by employing techniques like eye movement, EEG, and fMRI. And I also changed my tooling a little bit, started to use quite a lot of MATLAB. And at the time, I started to grow a strong interest of this kind of permutations and numerical approach, which kind of like introduced me to Bayesian. And I started to also move all my works into Python and PyData, kind of these ecosystems. And I especially interested in MCMC methods, kind of like a continuous of my love for bootstrap and permutations. And around a little bit more than a year ago, I changed my career again and switched to industry. So currently I'm a data scientist in Google, working mostly on user trust and working in trust and safety, mostly kind of like protecting users, make sure that the platform is clean on Google. And today I will talk about how to implement a Bayesian or probabilistic library in Python. So first, some disclaimer. Although I work quite closely with Tensorflow and Tensorflow probability team, my opinion does not, I'm not a spokesperson for them. I don't represent them. And also, I'm not a software engineer, so I will be talking quite a lot about like implementing, writing software, but it's more from kind of like personal experience as a data scientist and as a PyMC developer. So we'll first go through, for today, just a quick outline. We'll first go through some basic building blocks of writing down a Bayesian model. For example, what we would need for implementing a probabilistic library, and also I would mostly focus on how it's currently done in PyMC3 and why we need to kind of find a new approach for PyMC4 or moving forward. And I also will touch a little bit around this concept called effect handling. For example, like it's mostly about when you write a program, how you handle the side effect correctly so that you get what you're actually intended for. And as some expected takeaways, be able to write your own Bayesian library is not one of them. Instead, I hope that it will give you some better understanding of how a probabilistic library is implemented, so that in a way, when you write down your own Bayesian model or probabilistic models, you now have a better understanding of how I should debug it. And basically also a better strategy in terms of when you are changing your model or when you read some codes of other people implement a model, you have a better understanding of, oh, why did they do it this way? And if I want to change, how can I make sure that it's running correctly? So right, Bayesian modeling. I actually will not give any introduction on Bayesian modeling, so, but in just a really, really high level, we can think of all our data that we are trying to analyze, trying to model is from some generative process. For example, if you look at the first figure here, we can think of that you have this observed data, it's just coming in as a one-dimension array. And if you do a histogram, you have this kind of shape. And actually, this data is generated from a mixture kind of distribution. So in kind of like the key thinking here is that you have some observed data, and they are actually generated from some random process. And we try to write program to capture this generative process. And kind of like the main tagline of being a Bayesian is that not only we are thinking of the data we are observing as coming from some generative process, but also the parameters. So all the parameters we are trying to model for it as, for example, if you look at linear regressions or some scatter plots on the right, not only we can think of it as a generative, kind of like from some generative process that is linear, we can also think of the parameter in this model, for example, the coefficients, the intercepts, they are also coming from some distributions. So that's kind of like the general idea of why we want to do Bayesian modeling and how we can think of our data as from some Bayesian model. And you might have seen some representation of Bayesian models such as the following. In general, it's a very expressive representation. And us being a Bayesian, we like to claim that you can write down any model as a Bayesian model. And sometimes you might recognize these kind of notations. So if you go line by line, it will mean that you have some parameters is kind of from Gaussian prior. And you also have another parameter is from a half normal or half Gaussian prior. It means that this parameter will only define for numbers that are positive. And then you have some operation here, and then at the end, this is your observations. So again, this model here explains the linear regressions that we just see. And you can also represent it in another way of this kind of graphical model. And in this way, it kind of spell out the dependency more directly. So this is actually some of the graphs that you can generate when you're using PyMC3. So you can just draw the graph. And here what it tells you, it actually has some additional information. For example, here it tells you there's 100 observations. And there's also a linear transformation, although the tilde is not strictly correct because it's the deterministic transformation. So on a very high level, an ideal Bayesian library should provide a consistent, or what I like to call a no-surprise API to express this kind of model, and we can get useful information from them. So what kind of information we want to get from a Bayesian model? Here would be some typical things that I or any kinds of people doing analysis might want to see. For example, we want to identify what are the unknown parameters in my models. I want to generate a posterior distributions. You sometimes call it the loss function when you're doing optimizations. And this, we will use that for our inference. And the point here is that sometimes not only we want the full posterior, sometimes you want, for example, a conditional one or a marginal ones, which means that some of the dimension actually we treat it as different than the others. And we might also want to evaluate a function over the posterior distribution. And these are in general the cases when you have an objective function and you want to use the posterior to make decision. For example, if you know that the hurricanes, how likely it's going to hit the city, and you have an objective function like, oh, if it does hit the city, how much loss we have, and whether we should evacuate the city. And these things, formally, it can be described as applying this objective function over the posterior distribution. And usually in practice, we'll try to sample from the posterior and use Monte Carlo sample as a representation of the posterior. And last, we also want to get the conditional probability and use that to do random number generation. These are use case, for example, you want to do posterior predictive sample, which means after you fit the model, you want to see that how the uncertainty around the observation is, given the model that you just fit. And yeah, and a bit more. And if I kind of summarize all the things that we typically do on a Bayesian model, we can kind of think of it in two ways. So one of the way is that we run the program forward of this kind of forward generative or simulations. Basically, what it means here it would be we simulate from the prior, we plug it into any kinds of functions, and then we have the likelihood or the distribution for the observed data, and then we generate the kind of this fake data. And the other way to think about it, of the things we want to do or what we want to get from a Bayesian model is this kind of backward inference, or we want to get the likelihood or the loss function. And this usually means that we actually have some observations and we want to inference the unknown parameters. So basically the information is kind of floating from backward to the top. So now, the first task we will have to do is, of course, we want to translate this model that we write on a piece of paper into something that a computer recognizes and can run. So let's try to first kind of identify the operations and see how straightforward it would be to implement it. So the first things that we can kind of see is this numerical computations. So there are a lot of, it's kind of like straightforward because in the Python data science or Python PyData ecosystem, we have lots of scientific computation tools. We have like the classical like NumPy, SciPy, and we also have things that comes with gradient like TensorFlow, Pytorch, and so on. And for example, here we will see that we have a matrix multiplications, and we have additions. So that's kind of like one of the, among some of the common operations we want to do or functions we can apply. And usually, for any kinds of numerical computation tools or library that we are using, it comes with some representation of data type. And for example, you can have flow 32 array, or you have tensor, which is a high dimensional array, although the definition is debatable sometimes if you talk to mathematicians. And also you have a collections of like domain-specific toolbox that is built upon the this kind of more elementary numerical computation tools, so that you can have like complicated function transformations. And then the next things that we can identify are the distributions. So probability distribution, I'm not going to go into detail like what is the formal definitions, but on a high level, we can understand it as something associated with a random variable, and it usually comes with a probability function, is either a CDF or a PDF, which means that you can evaluate on kind of like accumulated probability, or you have a probability density function that you can evaluate on some inputs. And it also, most of the time, it comes with some random number generations, so you can generate random number quite efficiently. Right, so the last piece is kind of like the most difficult, is the random variables. And the reason of it being difficult is that it's actually not really well defined if you actually try to write down some program, for example, in SciPy. So I will skip the definition for now, and let's just look at how SciPy is kind of defined what a random variable, and we try to use that to express this probabilistic or this Bayesian model. So in SciPy, the stats module provide a lot of distributions, and if you look at the docstring, it actually says that they define a random variable. So for example, here there's docstrings for the normal distribution, but actually it says it's a continuous random variable. So yeah, let's go ahead and try to use it and see what happens. So now what I would do is I will start writing out this program, kind of translating this Bayesian program into a Bayesian model into a program. So for example, I just give it some random data, and then I spell out all the distributions. Now the error happens when I try to plug that into a linear equation or any kinds of functions. Because it will complain that the type is actually not supported because you cannot multiply kind of like a NumPy array or this array data type with a random variable, a frozen random variable. So it turns out that depending on the operations of any kinds of numerical method, it actually only defines on some specific data type. And if the data type is not kind of compatible, you cannot propagate your program. And that's kind of like down to the core of why it's difficult to implement a Bayesian model, because it actually changed the value or the representation of a random variable in actual computation. It changed depending on what things we want from it. So in a way, it's that depending on what mode we are running, the program is executed differently. So by what I mean is that we can look back at what we started out of, like things we want from a Bayesian model. So we want to do this forward generations, and we want to have this backward inference, a loss function or posterior distribution that you can evaluate on. Now, so if you want to have a program that actually runs in SciPy, you will actually write this way. So here is kind of like still the same. So you define, you kind of have a frozen random variables. But if you want to plug that into a linear functions, actually you need to draw some numbers. So which means that now you have some visualization of these distributions. And after you do this, draw this random number, this now is some NumPy arrays. So you can do multiplication, you can plug it into a function, you can do things, it's just like what you normally do, right? And also for generating the kind of this prior predicted distribution or some simulated data, we also need to do the samples on the likelihood or the distribution that define our observed data. Now, in a reverse mode, that is a bit different. We still have the distribution kind of defined it the same way, but now we actually need a function, because all the unknowns that we want to evaluate, we actually don't have the actual number yet. So basically, we need to give it some kinds of placeholder. And the best way to represent it, of course, is a function, because then we can plug it into any kinds of inputs. And now, because these are implicitly, they need to be something that they can, you can do computations, or you can multiply, you can do the you can do the matrix multiplications, you can do additions. So there actually needs to be some kinds of NumPy arrays in this context. And then you actually also run it differently in a way that you are not doing simulation, but you are pulling out the class method, which is the log plot, and then you compute it, evaluate on the numbers that the user input. So that's kind of like the main challenge. So we have the kind of the numbers that we want to propagate in this program come to this point. The number actually comes from different places. So they, in a forward kind of mode, they're coming from some random draw of the distributions. And in a backward computation mode, they're coming from some user inputs. And you might say that, oh, actually, we can just combine everything together, and you can write this huge code, basically, depending on the context. So for example, oh, the user wants to have some forward mode, and we do something different. If the user have a backward mode, we do something else. And now this program will be fine, because you can just initialize this kind of function to generate another function, and you can use these callables to do simulations, or to use it as log plot functions. And of course, this is really unsatisfying, especially when you look at the code. You see, oh, all these are completely the same. So why can we not just combine them together? And that's kind of like the things that we want to achieve in a good Bayesian library, is that we want to combine these two processes into a coherent API. So which comes to this is our challenge. Oh, sorry. Which means that we need some kinds of placeholder. They should just act like a NumPy array or any kinds of tensor, depending on the backend you're using. And you should be able to kind of swap out the values underneath depending on the context. So again, if the user is running in this forward mode, then we would we'll do a sample from distributions and then plug that in. And if user actually supplied in these values, then we just use those values. So what are the solutions? Of course, the no-brainer is that you use you ask the user to provide this log posterior distribution directly to you. So, which means that the user, if they want a simulator, they write a simulator and provide it to the library. And if they want a log-plot function, they spell out the log-plot function themselves. And this is actually some of the approach that some probabilistic library use. For example, EMC is you need to provide a log-plot functions. Also, if you use low-level TensorFlow probability, you also need to do the same. And the pros is that now we don't need to worry anything, as building a library is easier than ever. But the cons, of course, you rely on the user to do the right things. And writing this thing twice is at best kind of tedious and at worst buggy, because user might provide inconsistent programs. There's the implementation is not the same in the two, but it's very difficult to validate. So what is another solution? So another solution is this idea called a deferred executions, which means that user write down a program, but we don't execute it yet. And depending on the context, we will execute it, and we use the value that depending on the context. And this is what essentially the TensorFlow distribution of tensor probability joint distribution does. For example, in joint distribution sequential, you provide a sequence of distribution and lambda functions, and given that they can be initialized depending on the context, now when people are asking for a log plot, then they just regenerate a log plot on the fly. And also, this is what the PyMC4 prototype 2 V2 doing. So we actually draw quite a lot of inspiration from the joint distribution coroutine. And the good thing of here now is that you have a really coherent framework. For example, for TensorFlow probability, in the joint distribution class, actually it adds, behaves just as if you're using any other kinds of distribution. And that is by design, so which means that you can pass it around. And there are some kind of corner cases, of course. It's not completely the same because the usual distribution, it outputs a tensor when you sample, and in the joint distribution, it outputs a list of tensor. But at least in the API level, it behaves, from design, they try to make it behave the same. And kind of the cons is that now you need to have this lambda function, and you don't have the random variable. So if you want to just get one of the components from the model, it's really difficult. It's possible, but you basically need to run the whole program and then just do indexing to the list of the things that you want to basically get this kind of random variable concept. And the first solution is that you can implement a random variable class and make sure it kind of does the right thing, a huge quotation mark. So right now, this random variable, it needs to act in a way kind of like a placeholder, so which means that it either has a property of a tensor array or its object behave like a tensor. You can, for example, overload is operators, or you can inherit a class that is a data type with all the right operators. And you also need some mechanism to detect the context and modify the program at runtime. And right now, there are quite a few probabilistic libraries is implemented this way. For example, you have Pyro, you have Edward2. It uses some concept called effect handling in Pyro, and this kind of interception tracing in Edward2. But we'll come to that later. You'll see that they're actually conceptually very similar. And otherwise, you will need the random variable kind of carry is a Markov blanket. And Markov blanket is a kind of fancy term of all the nodes, it needs to carry its parents and its children. So basically, we know that for any kinds of random variable, who is its parents, what is the downstream trial. And then this makes sure that whenever in a different context, we can always trace back to the parents and trace back to the parents and then run the program again. So there are a bit more kind of like nuance to that as well. There's the additional kind of good thing of writing, having a random variable class is that now your program just looks and feels just like the notation you see. But the kind of like a big but is that it's not really, because it actually relies quite a lot of side effect, which means that you might think that your program is running this way, but it's not the case. There's something really funny happening underneath depending on what you actually ask the probabilistic library to do. And sometimes we call this feel like a spooky effect at a distance, because now what user write is not exactly what we are executing. So now I would go on to explain how we kind of solve this problem in PyMS3 in the old days. Well, it's still the same implementations, but because the deprecations, now we need to find new ways. So in PyMC3, we have the concept of that a random variable is actually a Theano tensor, because we use Theano as our computational backend. And we have this kind of like abuse of a context manager, because we used to get complained that, oh, why are you doing this? And we basically use that as a generation of side effects to compute the log plot. And we also do some graph management through Theano. So it has some kind of like, for example, use Theano.clone to clone the input of a graph. And this turns out to be really powerful. So PyMC3, in a way, is tightly integrated with Theano. And I will first show you what kind of like a distribution is implemented in a PyMC3. So we have the random number generations is actually a generator written in NumPy and SciPy. And we also have a log plot function. And the log plot function is always evaluated at runtime, so which means that we always get back a Theano tensor at the end. But the funny thing is that how we use this distribution is that if you look at kind of the meta class of distributions, actually we always look for the model context. So if you initialize a distribution, we make sure that it's always underneath a model context. And if they are created outside of the model context or the context manager, we will raise an error. And then if, depending on the specificity, we now would initialize the kind of like the stateless distributions and associate it to the model by adding it to the variables. And here we will return either a free variable, so transform a random variable, and they are all act like a tensor. And so, for example, let's take free random variable as an example. So it basically enables and assigns the log plot probability to a Theano tensor, because now we have, when we define a class, we associate all the methods from a tensor variable. And we also give it this property that is the log plot. So kind of the magic here is that we evaluate the log plot on itself. Because now this is a tensor, it comes with some values. And when we evaluate it on itself, we build these dependencies, and we can compute the log plot correctly. So it's all sounds like a super magical, but don't worry, let's go through an example. So say that we have a rather simplistic PyMC3 model. We have some betas, which is comes from some distribution of 0 and 1. normal distributions. And we have X, which is, has a mean of beta and a standard deviation of 1. And we also have some kind of a deterministic transformation on the tensor, which we just square the X. So on the level that the user actually see, or on in your Python environment, what the program does is when it runs is that it first generate this variable is a Theano tensor, which is beta, and as a side effect of the PM.model, we will associate a log prop to this tensor. And then we have a second tensor is created. And now, because it has some dependencies, so we plug that into the distribution definition. And again, we evaluate it on itself and associate that property to the tensor. And then at the end, we have some other things that is user-defined, but because they are not contributing to the log prop directly, so they are just floating around. We might track it, we might not track it, depending on whether you have some PyMC3 wrapper on top of it. And just some quick side note on context manager. If these all seem too magical and too intimidating still, just remember that when you see some with statement, it's basically there were some setups, and then there's a user code that been executed, and then there's some additional thing at the end. And now we can see how log prop is generated. So the model now will collect all the random variables. Basically, this means that everything in the model doc free variables and observed variables, and also the potential terms. And then we will sum it all together to get the model log prop. And these are all still happening in the with context, kind of like without the user realizing. And that's basically our model log prop. This is all the log prop information that we actually need in a backward kind of computations. And for convenience, we also will actually clone the input and flatten them into a one-dimension array so it's easier to work with. And then we'll combine this whole graph into a functions that we now use it as a callable for the computation of log props. So I actually used to think that Theano.clone is the things you must have, but actually it's not the case. Basically, the real magic here for using Theano and in PyMC3 is that we can compile a Theano function, and this function is actually crazy fast. So which means that now we can use this function to, we can write everything else in NumPy, because this function is just as fast as a NumPy functions. Right, so this is kind of like all the things of to get the right log prop for PyMC3. But what about kind of like these forward generations? Actually, things are much more complicated in this case because we ourselves didn't implement any this kind of random number generation in Theano, which means that we actually relied it on the random variated method from a SciPy distribution. And we do some kind of graph travel shell to draw from the parents and make sure that we do the conditioning correctly. And the big problem of that is we got a lot of shake and broadcasting issue. So at some point, I make the joke that 95% of the problems on PyMC3 is shape related, and the rest 5% is basically how to install Theano. And here I would like to give a big shout out to Luciano. He has been doing a tremendously great proportion of work to basically fix our shape handling in forward random generations. So now our shape error is cut down, I would say probably half. And he wrote this blog post, I would share the links afterward, basically explaining what the difficulty comes from. So in a way that it's not our fault, because the SciPy kind of shape handling have some kind of like needs some improvement, because it doesn't distinguish some of the more specific shape requirement. Right, so some reflection is on our side for PyMC3 is that by using this kind of complicated compile Theano functions, it allows us to move pretty fast because all the MCMC method, actually, all the samplers are all written in Python and NumPy. This makes the contribution super easy because everybody, most of us, even kind of, if you don't know much of like more complicated frameworks like Theanos or a Tensorflow, NumPy is something that we are quite comfortable with, and it makes people really easy to contribute. But the downside of it is that it's quite difficult to take full advantage of GPU, because when we are running some things that use GPU through Theano, and when we do sampling, you actually need to communicate all the data back to CPU, and this communication is really costly. And we also use some graph editing and cloning to allow us to do something quite fancy. For example, for the variational inference, we actually make great use of that. And it also relatively easy to debug because in our case, all the random variables are exposed in your environment. So you can check, for example, what is the tensor underneath. You can check what is the kind of like the test value that is currently carrying. You can compile even the condition on all its parents, compile the log plot just up to that node. And of course, the big drawback is shape issue, because actually the funny story is that we used to have this discussion to say that, oh, should we introduce a better shape system to distinguish when people try to broadcast and versus when people actually want some kind of independent draw from the same distributions. And that's, at the time, our decision was no, actually just one shape is fine. And now we are basically paying for the downfall of that. So as good as Theano is, the bad news is that it's currently deprecated. So after some soul searching and some basically look around of what other alternative we have, we now turn to TensorFlow Probability. Is a build by Google, by part of the TensorFlow team. And it comes with all the kind of necessary components we need. For example, it comes with distribution, it comes with bijections, which is one type of transformation, but is volume preserved. And also it comes with inference method like Monte Carlo samplers and variational inference infrastructures. And this gives us quite a lot of new and exciting opportunity. Something that I'm really excited about is that they have an absolutely amazing shape system. So basically you distinguish between sample shape, batch shape, and event shape. Although I would love to talk about this, but we don't have time. But I highly encourage you to kind of search it and see why it's important and why you should get excited about it. And also it has better hardware support, it has better binding with deep learning. If you want to do Bayesian deep learning, now it's easier, it's under active development, and everything is in the graph, including inference, which means that now hardware acceleration, we can do it on everything. There is no need to, if we are running on GPU, everything is on GPU. There's no need to communicate back to CPU. And at the time, something that I'm extremely excited about is that they have the sample method also being in the graph or also being in TensorFlow, which means that now we can have this kind of symbolic samples. And if you write down something like this, you just sample from a distribution. So you set up a distribution, you sample from it, and then if you, in a session, you can repeatedly run this session, and every time you get back a different result. This means that if you want to run experiments, you want to do this kind of simulation-based method like likelihood-free inference, it suddenly becomes much easier to work with. But unfortunately, this API is deprecated because now we all move into TensorFlow 2. However, good news is that the TensorFlow probability team is actually working really hard to fix some of the problem. It's now have a new class called a transform variable, which is used to call a defer tensor. So the idea here is that you don't immediately execute the tensor unless the user asks you to. And now these things should work. Basically, you can take gradients of the the random samples. And I think you can, but what doesn't work still is that you cannot sample outside of a gradient tape and keep taking gradient of it, because it won't get updates the next time you run it, as it's not in the graph. It's an eager execution mode. So yeah, so it comes up with some new challenge. I mean, everything is in the graph, so potentially everything is going to be awesome. And the API needs to be kind of this idea is called tensor in, tensor out, which you always, you need to think of it, everything input should be a tensor, and you get the tensor as an output. However, this means that some of the strategy, as in PyMC3, is not going to work anymore. So for example, in the early days, we were saying, oh, since it's a compiled graph, maybe we can do something similar. We can get the tensor, for example, the log-prog tensor, and then we just do this feed dictionary. Basically, we can evaluate on a new set of input. However, that is not going to work in TensorFlow 2 as well, and at the time, it was also too slow. So we really need to think of a new strategy. So basically, the strategy here is that we need to find a way to generate a function, which is now we come to a domain, is some kind of meta program. So basically, we are not writing a program to walk the graph and compute a log-prog, but actually we are generating a function, and we use that to compute as a function to pass it around. So this comes to the kind of like the points that people want nowadays in the kind of the cutting edge development. We have this thing called effect handling or tracing or interceptions. So in this context, all the models now you write they are functions, because functions you can basically read execute it. So the idea is that depending on the context you are running, you read execute a program, and then you just swap out the value inside depending on what kind of computation you do. So recall that, because in the forward context and in the backward context, you actually want to substitute this kind of tensor value differently. So you still write a models that looks very similar to a PyMC3 model or a model that you write on a piece of paper. But now, because it's a function, sometimes you don't get immediately, you might not be able to immediately get these random variables. And to generate a log-prog functions, for example, in Edward 2, it comes with this helper function. Basically, you pass a model. Now, recall that this is a function. And it do some interception, and then you get back a callable. Then now you can pass the values and the dependency to get the log-prog. So how does it actually work? So this is kind of a code that is actually using. So I want you to focus on here. So here what it does is that when you pass, you have this a kind of dictionary, and it gets the name. The name here are the names that we assign to each random variables. So because it has the name, now you can do this lookup of the names, and you just swap the values, and you substitute the value here. And then afterward, you still evaluate on itself, similar to what you might have done, you see earlier in a PyMC3 program. And you just, at the end, collect all the log-prog, and then you do the sum of it. And the magic, again, here is what we call a trace. So the trace basically is that, because it's a context, and remember that the context is that you run a user code, but every time you actually do something additions. And this addition thing is what the tracer is doing. So implicitly, it swaps out the values, and it evaluates the log-prog on itself. And this is what a trace kind of program looks like. So basically, in a very high level, it collects some information from the previous executions, so that when you evaluate it, you can always kind of regenerate this random variable, but now with the correct or the dependency that the user actually input. And there's also a similar concept in Pyro, and they call it tracing. And the key signature they use is this. So what it does here, it actually generates this order dictionary. Basically, it's kind of like a tape machine obtain like, oh, what is the sequence of the program being executed. And then what they do is that when you're running inference or when you're trying to do a conditional, it will also swap out the values. So here is one of the, they call it a portin. And one of the things that they use is this called replay messenger. So basically, in a high level, is that it replaces the value so that it evaluate. So it generates the Bayesian program correctly. In this way, the Bayesian program is either in the forward context or in the backward context. And then, because now the values are all updated, you can evaluate it, get the correct result. And these are actually also, in the beginning, the approach of what PyMC4 is using. So we use this kind of interception, but we give it only two contexts. So unlike Edward, that we have like any context you want, we just have a forward context, a backward context, and then we do this replace of kind of like swap out the values on the runtimes. But now in the PyMC4 version 2, we actually use something different. We now intercept the control flow with Python coroutines. So I'm not going to go into too much detail of coroutine. We actually recently submitted to a workshop of NIPS. And you can, I will share the link afterward. If you're interested, you can have a look of the paper. And what it does here, again, is basically based on the context you run, you want to swap out the values. So that is still the same. So you have started out with some placeholder. And then when we'll try to see that if we can use this value directly to interact with the model. And if that doesn't work, we'll do something else. And you can see more information on the link here. And again, the key point here is that this control flow now is kind of doing the right thing, depending on the context you're actually asking for. Because if the user are supplying some values, it actually rebuilds this computational graph so that you have the correct log-plot functions. Right, so that's more or less it of kind of in a more really general way, what is the current direction of implementing a probabilistic model is basically do this kind of interception. The powerful way, the power of doing that is now is really universal and is extremely flexible. In theory, you can use any kinds of backend, which means you can use Tensorflow, you can use a Pytorch, for example. Pyro, they have the Pytorch and JAS backend, and Ever2 has implemented TensorFlow and NumPy backend. But kind of downfall is that it's quite unintuitive. So I'm sure that you're super confused after in the previous few slides of all the effect handling and how it's actually executed. And even for me, myself, I mean, on a high level, I understand it completely, but if you want me to debug it, it's a pain because it does these things that basically, when you first run it to generate a program, it might not give you any error, but when you actually evaluate it, now you have an error. And because it's this kind of meta programming, you have lots of trouble of debugging it. And also because it has, the majority is kind of like side effects, so it's even to the user, if they don't want to know, it's fine, but if they want to kind of like get a better understanding of how it actually works, it seems even more magical. In a way, it's kind of like you are implementing your model, but you're not interacting it directly, you are interacting it through this glove box, and just hope that it works. But there's also another approaches. So for example, you can do something crazy like an abstract syntactic tree. So basically now you kind of like just write a text file, and then the text you have a program to read the text files and compile a model for you. Or you can do graph managing yourself. And for example, you can use something like already available on a graph library. And what you might need to do is to wrap the operator so that you get these deferred executions. And the plus side of it is that you have maximum control, and the library will be really low level because you can do graph optimization yourself, and you can do this graph combination. You know the computation sequence completely. But the downside is that, congratulations, you are just re-implementing TensorFlow. But all jokes aside, actually, we have some serious effort that leading by Brendan on the symbolic PyMC, which is something that I'm very excited about. And you can have a look of the repository and see what is the current progress. Right, so I think I'm 50% done. So basically now, if you follow this recipe, you can implement a library up to 50%. And actually, 45% would be implementing distribution and transformation like bijections. So what are the rest to do if you want to implement a Bayesian library is that you will need to implement inference method, for example, optimizers, Monte Carlo samplers, variational inference. And you also need visualization and diagnosis, but now we got Avis, so you actually can skip this part. And you also need testing. And unfortunately, testing and benchmarking or writing benchmark model for probabilistic models, they're really, really difficult because you are dealing with some stochastic programs. So which means that you get a different result almost every time you run. And so how do we can make sure that it actually runs? So there are formal validation method like SMC, so it's simulation model calibrations, I think. And also you have this question of, oh, do I seed the test or do I not seed the test? Because if you seeded the test, if the seed is kind of like just randomly make your test pass, then you're screwed. And if you're not seeding a test, then you might get false positive a lot of time. And in general, Monte Carlo central limit theorem is your friend. So, but it means that you also need to run your, for example, a Monte Carlo sampler like lots of times. And if you have an expectation that is undefined, which means that you are screwed because you don't have the central limit theorem anymore. And some difficulty that I encounter, for example, is people can be related too much. People, I mean me, I was related too much on multivariate normal, and especially diagonal multivariate normal, so it's especially bad. And also, I encounter bugs that they just impact the efficiency but not the correctness. So suddenly your test still passed, but it takes twice as long, and you were just like, what? And you can have, sometimes you want to implement an algorithm change, but really it improve efficiency in some model, but not the other. And you're like, should I still implement it? Or should I have like more complicated logic to do this switch in the middle? And also, at least some of my, from my experience, that is you really need integration tests and as early as possible. So so as some summaries, I hope I convince you that it's quite difficult to write a Bayesian model in library. And the most difficulty, kind of like the 5% of the work, but it's 90% of the time you spend in this long tail event, is that you are actually need to think about, because the Bayesian program can be executed in two ways. Now, how do you make sure that it runs correctly in both? And we can build quite flexible framework by using this deferred execution, but the difficulty is that you are dealing with this indirectness. And but in general, I think that it's also kind of like a good direction to moving forward, because you can do things, more complicated things, potentially easier. For example, if you want to have complicated conditionals, or you want to have this dynamic graph, now it's much easier. Right, so that's all for me today. I would like to thank the people from PyMC organizations that all this year working tirelessly of building a better probabilistic programming environment. And also thank you all for your attention.
Bueno, ¿preguntas?
There is a part I did not understand very well. I don't really get why you have to create a function that writes a function. Like, why do you have to do metaprogramming to evaluate the graph? On you can write directly a function that does it.
Yeah, so if you write directly a function, that's kind of like what, if you use low-level kind of API does, because now you write your function directly, right? So the kind of difficulty here is that you actually not writing I mean, in the new ways of writing, the model, it is a function that you can kind of repeatedly execute it. But if you want something kind of like closer to what you see in the notation, which means that you just have, for example, a Jupyter cell, a cell in a Jupyter notebook. You write down all the random variables, and then you just do computation, and at the end you evaluate the log plot. That means that you actually need some way to generate a function, and that's kind of like the tricky part, because now you need the callables that you can plug numbers in, but not just kind of like the result at that point when you execute sequentially the log plot. Yeah, I know this point is a bit difficult to wrap your head around, because I think the main difficulty is that when you think of when you actually write down a log plot functions, you see how kind of like how different or how not different it is with a Bayesian model. So in a way that if you only want the log plot, that's fine. And that's actually a valid thing to do, that you just write down the log probability. But the problem is that when you try to have this higher level API, like for example, Keras, and it turns out it's really difficult to build a probabilistic programming library on top of Keras, because it's all sequential, and you also have like nodes that not directly related to your input. So you actually kind of like create these nodes out of thin air, and you actually need some, you need to inference those nodes, and they're not related directly to your input whatsoever. So now you have this difficulty of that, oh, how do I keep track of them, and how do I swap the values into the graph correctly? So that is mostly the difficulty, and that's also why nowadays people prefer to have this deferred execution to generate a function instead.
¿Alguna pregunta más?
You want to provide a bit more information about you mentioned about the central limit theorem for testing stochastic programs, please?
Yeah, so I mean, central limit theorem is like when you compute the means. If you compute with some, well, I'm going to be fact checked really hard on this, but basically it's like if you have some estimator computing the expectations, in the long runs it will approach to some kind of Gaussians. And in the Monte Carlo kind of central limit theorem is that you still have some similar things, but the standard error now is related to the Monte Carlo estimation errors. So because this things is Gaussian, so it's you can now evaluate it. For example, some of the tests I wrote on using that is that I would run a samplers, and then I would do an estimation of some parameters. And in this case, because I know what the true parameter is, so I just compute like the Monte Carlo errors, and then I compare it with a normal distributions, and see if the kind of like the differences of the estimation, whether is within some margin of error. So for example, is it 5% of errors, or is it even more?
¿Alguna pregunta más? Bueno.
A really small comment for everybody. Those that never used PyMC3 and have a rough time understanding this type of things, I highly recommend you check out Bayesian methods for hackers. It's really easy to understand. In 15 minutes, you get how practical all this stuff is, or why this work is really useful when you want to do practical stuff.
Yeah, thanks.